Dear student, previous class I discussed about the nomenclature of coordination compound, rules for writing, formula of a coordination compound, problem related to the coordination number and oxidation number, and finally I discussed about the effective atomic number rule. Now I will discuss about the Valency bond theory. Shortly it is called VBT. It is an important long question. This theory is used generally to explain the structure of coordination compound or complex ion. Suppose I will take a complex ion FeCN6 3-. To explain the structure of this complex ion, generally we need the postulates of Valency bond theory. So at first I will discuss about the postulates of Valency bond theory. What are the postulates of Valency bond theory? The first point is the central metal atom or ion makes available number of orbitals which is equal to the coordination number of the central metal atom or ion to accommodate the electron of the ligands. Second point is the central metal atom or ion uses hybrid orbital involving s, p, d for accepting the electron of the ligands. Third point is the ligand must have at least one sigma orbital. Fourth point is the vacant hybrid orbital of the central metal atom or ion overlap with the fulfilled orbital of the ligands to form metal coordinate bond ligand sigma bond. Next point is the d orbital used in hybridization and also to accommodate the ligand electron may be ND outer orbital or N-1 D inner orbital. Next point is the Hund's rule is applicable to the electron present in the non-bonded orbital. Next point is the number of unpaired electron can be calculated from magnetic momentum measurement. Magnetic momentum mu equal to root over of n into n plus 2 Bm. Here n is the number of unpaired electron, Bm is the Bohr's magneton. Next point is by the help of number of unpaired electron and the magnetic momentum we can able to determine the shape of a complex ion or coordination compound. Next point is under the influence of strong field ligand, the unpaired electron may get paired up against the Hund's rule. These are the postulates of Valency bond theory. Now I will explain the shape of this complex ion by the help of postulates of Valency bond theory. Let me explain about the shape of octahedral complex. There are two types of octahedral complex. One is inner orbital complex. It is considered as generally low spin complex. This is an example of inner orbital complex. For inner orbital complex, generally we need T2sp3 hybridization. So our first aim to form 6D2sp3 hybrid orbital. Then I can overlap the fulfilled orbitals of the ligand within the vacant d2sp3 hybrid orbital of the central metal atom or ion to form metal coordinate ligand sigma bond. To explain the structure of this complex ion, at first I will draw the electronic configuration of central metal atom. Here the central metal atom is your iron, and iron having atomic number is your 26. The electronic configuration of iron is your argon 18, 3D, 6A, 4s2. This is the electronic configuration of iron. Here 5 orbitals are present, so I can distribute the electron like this. This obeys the Ohm's rule. Here also 2 electron is present. The 4p orbital is now, look at that, it is in vacant condition. Our aim to form 6A vacant d2sp3 hybrid orbital. In this case, here iron present in Fe3+. Look at that, Cn having oxidation state, that is -1. There are 6 Cn minus, so you can write here -6. As a result, it is bound to write here +3. That means the oxidation state of iron in this case is your +3. Here Fe+3 act as a central metal cation. So next step is your convert the iron to Fe3+. It can be possible by removing 2 electrons from 4s orbital and 1 electron from 3d orbital. As a result, I can write like this. Here 1 electron, here 1 electron, here also 1 electron, here also 1 electron. And this orbital is now empty. This 4p orbital also in empty condition. For this complex we need 6 vacant d2sp3 hybrid orbital. For the formation of d2sp3 vacant hybrid orbital, generally we take 2d orbital from 3d and 1s orbital from 4s and 4p orbital. Next step is to form 2 3d vacant orbital. This is your ground state of Fe. This is your ground state of Fe3+. Next step, I want to form 2 vacant 3d orbital. This can be possible by the help of shifting this electron to this orbital and also shift this electron to this orbital. This goes against the Ohm's rule. This can be only possible by the help of strong field ligand. We know that under strong field ligand, the unpaired electron get paired up, which undergoes against Ohm's rule. Next step, I will write the excited state of Fe3+ like this. Argon 18. This is your 3D. Now I can write here 2 electron. Also I can write here 2 electron, and there is a single electron here. This is your 4s. This is your 4p. Look at that. There are 6 vacant orbitals are present. Now I will take these orbitals for hybridization. That means I can write here D2 sp3 hybridization. After hybridization, now I will attach the 6 ligand to this 6 vacant D2 sp3 hybrid orbital. So in next step I can write FeCN6 3 minus argon 18. This is your 3d orbital. Here I can write 2 electron. Here also I can write 2 electron. This is your unpaired electron. Now I can overlap the fulfilled orbital of the ligand with the vacant hybrid orbital. Now the ligand donate electron to the central metal atom. So here I can write 2 cross sign. These 2 sign indicate 2 electron of Cn, and I will form a bond with the central metal atom. Like this I can also write here 2 electron Cn. Here also I can write 2 electron. Here also I can write 2 electron. Like that I can write this. Experimentally it is seen that this complex has 1 electron. Look at that, here 1 electron is present. From this it is clear that number of unpaired electron, that is called n, equal to 1. So the magnetic momentum mu is equal to root over of 1 into 1 plus 2 bm. That means mu equal to root 3 bm. Since this complex ion having 1 unpaired electron, so the magnetic character of this complex is your paramagnetic. The structure of this complex is your octahedral. You can explain other inner orbital complex by the help of gravity. Now I will explain about the outer orbital complex. Outer orbital complex are generally high spin complex. Let me explain this with an example. COF6 3 minus. For the formation of outer orbital complex, generally we need sp3 d2 hybridization. This d orbital is your outer d orbital. In this complex, the cobalt exhibit in +3 oxidation state. So I will write the step 1 like this: cobalt 27, argon 18, 37, the 7 electron present like this. Next I will write the 4s having 2 electron, 4p is vacant, 4d also vacant. We do not take this d orbital for the hybridization sp3d2. We generally take this d orbital because here the d orbital must be your outer d orbital. In COF6 3 minus CO3 plus ion play an important role. So next step I will draw the ground state of CO3 plus argon 18. I can remove the 3 electron, 2 electron from 4s, 1 electron from 3d. So I can write like this: this is your 4p, this is your 4d. This is your ground state. Now I will do the sp3d2 hybridization like this. This is your sp3d2 hybridization. After sp3d2 hybridization, here 6 sp3d2 hybrid orbital are present. So I can form the CO L6A 3 minus ion complex like this. Argon 18, this is your 3D orbital electrons. These orbitals are considered as a hybrid orbital. Now I can overlap the field ligand orbital within empty hybrid sp3d2 orbital. So I can write like this. These are the electron of fluorine. I can coordinate 6A F atom or ion with the central metal atom like this. Experimentally it is seen that this complex have 4 electrons as unpaired. So from this diagram it is also proved that this complex have also 4 unpaired electrons. So I can write number of unpaired electrons equal to 4. So the magnetic moment of mu equal to root over of 4 into 4 plus 2 Bn. So I can write 4 into 6 root over Bn. That means I can write root over of 24 Bn. The structure of this complex is your octahedral. There are 4 unpaired electrons are present, so this complex is highly paramagnetic in nature. Next I will explain about the tetrahedral complex. For the formation of tetrahedral complex, we need sp3 hybridization. Let me explain this with an example. NiCO4. In this complex, nickel exhibit in zero oxidation state. At first, I will write the electronic configuration of nickel. Nickel having atomic number 28. So I can write argon 18, 3D8, 4S2, 4p0. The 8 electron present in 3D orbital like this. 2 electron present in the 4s like this. The 4p orbital is vacant. This is your ground state. We need the 4 sp3 hybrid orbital. For sp3 hybrid orbital, we need 1 s orbital and 3 4p orbital, and the orbital must be empty. So in the next step it is bound to shift these 2 electrons to 3d orbital. So I can write the excited state of nickel like this. Argon 18 in 3d orbital, the electrons are arranged like this. Now the 4s orbital is empty. Now I will subject this 4 orbital to sp3 hybridization. This is your sp3 hybridization. After sp3 hybridization, there are 4 sp3 hybrid orbitals are formed. Now I can form the complex NiCO4 like this. Argon 18, your 3D orbital and the electrons are present like this. This is your vacant sp3 hybrid orbital. Now I can overlap the ligand CO with the vacant hybrid sp3 orbital. Here I can write to cross that denotes 2 electron of CO. I can write the other electron like this, and also I can show the bond between CO and the hybrid orbital of the nickel like this. Experimentally it is seen that this complex has 0 unpaired electron, which is proved by the diagrammatical representation. From this diagram, it is also clear that the number of unpaired electron n is equal to 0, so mu is equal to 0. Since there is no unpaired electron, so the complex is dimagnetic in nature. Dimagnetic in nature. The structure of this complex is tetrahedral. Next I will explain about the square planar complex. For square planar complex, we generally need dsp2 hybridization. Let me explain the square planar complex with an example. NiCN4 2-. In this complex, nickel exhibit in +2 oxidation state. So I can write the first step like this. Nickel having atomic number 28. So the electronic configuration of nickel is argon 18, 38, 4s2, 4p0. The electrons of 3D are present like this. The electron of 4s are present like this. The 4p orbital is empty. In this complex, the Ni2 plus acts as an important role. So I can write Ni2 plus. This is your ground state. This is also ground state. Next I will draw the ground state of Ni2 plus. It is bound to remove 2 electrons from 4s orbital, and I can write like this. This is your empty. This is your also empty. We need one inner d orbital. Look at that. Here the inner d orbital is unpaired. So remove this electron and place this electron to this orbital. So I can write the excited state like this. This is your excited state of Ni2 plus. Now 1d orbital is empty. This is your empty 4s orbital. This is your empty 4p orbital. Now I can take this orbital and this orbital and these two orbital for dsp2 hybridization. Here I can write dsp2 hybridization. After dsp2 hybridization, there are 4 dsp2 hybrid orbital are formed. So I can form the complex like this. Here Cn is present. Here also 2 electron present. I can draw like this. Experimentally, it is seen that this complex have no unpaired electron, which is already proved in this diagram. Look at that, there is no unpaired electron present in this diagram. So we can write number of unpaired electron equal to 0. So magnetic moment of mu equal to 0. Since there is no unpaired electron, so the complex is diamagnetic in nature. The structure of this complex is a square planar. Now I will discuss about the drawbacks of Valency bond theory. What are the drawbacks of Valency bond theory? First point is the color exhibited by the coordination compound cannot be explained by Valency bond theory. Second is it do not make a interpretation regarding about the magnetic moment of measurement. Third point is the thermodynamic and kinetic stability of a coordination compound cannot be explained by Valency bond theory. Fourth point is it does not distinguish between the strong field ligand and weak field ligand. Next point is it fails to predict the number, position and intensity of a band in electronic spectra. Next point is it do not explain the complexes of certain metal in a particular oxidation state have low spin, while other complexes of the same metal in same oxidation state have high spin. Take an example, CO NH3 6A 3 plus. It is a diamagnetic in nature, but CO F6A 3 minus is a paramagnetic in nature. Next point is your exact prediction of the structure of four coordinate complex, whether it is a tetrad or square planar cannot be explained by this theory. These are the drawbacks of Valency bond theory. Next I will explain another important long question, that is crystal field theory. Shortly it is called CFT. Crystal field theory also helps to explain the structure of coordination compound. At first I will discuss about the postulates of crystal field theory. First point is the transition metal atom act as the central cation. The ligand donate the lone pair to the central metal cation. The neutral ligand act as a dipole, while the anionic ligand are considered as the point charge. Second point is the bond between the central metal cation and the ligand is 100% ionic. That means there is a electrostatic force of attraction between the ligand and the central metal cation. Third point is the negative electron cloud of the ligand repel to the electron of the central metal atom. As a result, what will happen? Point 1. The valency electron occupies in those d orbital in which there is no attack of the attacking ligands. Next point is the degeneracy of the d orbital is lost. Next point is the relative splitting of the d orbital is different for different ligand. Fourth point is the magnetic character depends upon the number of unpaired electron and the extent of splitting of d orbital. Greater the extent of splitting of d orbital, lesser is the number of unpaired electron and lesser is the paramagnetic character of the complex. Next point is the shape of coordinate complex can be determined by the help of crystal field stabilization energy. Next I will explain about the octahedral complex by postulates of crystal field theory. For the formation of the octahedral complex, the ligand approaches to the central metal atom along the axis. So the orbitals which is present along the axis feels more repulsion by the ligands. There are 5 d orbitals are present. These are dxy, dyz, dzx, dx square minus y square, dz square. These 2 orbitals lie along the axis and these 3 orbitals present in between the axis. So for the formation of octahedral complex, these 2 orbitals feels more repulsion by the ligand. Before the formation of octahedral complex, the 5 d orbitals are present like this. This is your d orbital present in the metal ion. When the ligand approach to the central metal atom or ion, then the average energy of this d orbital increases. This is the average energy of d orbitals in spherical crystal field. After the formation of the octahedral complex, the dx square minus y square dz square orbital having higher energy than dxy, dyz and dzx orbital, because the dx square minus y square and dz square orbital feels more repulsion by the ligand. So here the degeneracy lost, so I can write like this. 2 orbital having higher energy, this is your energy level. This is your dx square minus y square. This is your dz square. Another 3 orbital present like this. This is your dxy. This is your dyz. This is your dzx. This is your called barycenter. This is your an hypothetical energy level, and this energy gap is denoted by del 0. That is your called crystal field stabilization energy. This part is your 0.6 del 0 plus 0.6 del 0. This part is your minus 0.4 del 0. This set of orbital is called EG set of orbital. This set of orbital is called T2G set of orbital. The splitting of d orbital into different energy level under the influence of ligand is called crystal field splitting. So here I can write splitting of d orbital in octahedral complex. If a strong field ligand will approach to the central metal atom, then there is more splitting of the d orbital. That means the del 0 value goes on increases. The splitting of d orbital depends upon the nature of the ligand. There are different types of ligand, and the ligands are arranged according to the increasing order of their strength in a series. That series you are called spectrochemical series. In spectrochemical series, I minus having less strength than Br minus, having less strength than SCN minus, having less strength than Cl minus, having less strength than S2 minus, having less strength than F minus. Like this we can arrange. At the finally I can write CO. CO having more field strength than other ligand. That means CO is more stronger field ligand as compared to other ligand. This is your called spectrochemical series. Suppose I want to draw the D1 electronic configuration, that means say one electron present in the d orbital, then it is bound to give one electron here. Suppose I want to draw the D2 electronic configuration, then I can write here another electron. For D3 electronic configuration, I can write this electronic configuration. Suppose I want to draw the D4 electronic configuration, then it depends upon two factors. One is pairing energy, another is crystal field stabilization energy. That means it has zero value. If the pairing energy is more, then the fourth electron is present here. If the pairing energy is less, then the fourth electron present here. For D5, if the pairing energy is more, then the fourth electron and the fifth electron present in these two orbitals. If the pairing energy is less as compared to the crystal field stabilization energy, then the fourth electron present here, then the fifth electron present here. Like that, we can also think about the D6, D7, D8, D9, D10 electronic configuration. If a strong field ligand is present in a coordination complex, then the del 0 value goes on increases. Then all the electron wants to fill up in the lower set of orbital, that is your T2G. As a result, the number of unpaired electron goes on decreases. If the number of unpaired electron goes on decreases, then the paramagnetic goes on also decreases. And that type of complex are considered as a low spin complex. If a weak field ligand approach to the central metal atom, then the del 0 value goes on decreases, and there is possibility of more number of unpaired electron, and the paramagnetic character goes on increases, and the complex is said to be high spin complex. Next I will explain about the tetrahedral complex. For the formation of tetrahedral complex, generally the four ligand approach to the central metal atom in between the axis, so the orbital present in between the axis feels more repulsion by the ligand. If you think about the d orbital, then dxy, dyz, dzx orbital placed in between the axis, so these three orbital feels more repulsion. As a result, the energy of these three orbital is higher than these two orbital in case of tetrahedral complex. So I can just change the diagram like this. Here dxy, dyz, dzx orbital are present. Here two orbital are present. There is your dx square minus y square, another is your dz square. This difference is called plus 0.4 del t. This difference is called minus 0.68 del t. This is your said to be del t. T means tetrahedral, O means octahedral. This is your barycenter. For D1, I can place one electron in this orbital. If two electron present, then I can place in this orbital. If three electron are present, then I cannot explain whether this electron present here or this electron present here. It depends upon the pairing energy P and the crystal field stabilization energy del T. If the pairing energy is more, then the third electron present here. If the pairing energy is less as compared to the crystal field stabilization energy, then the third number electron present here. Like that, you can also think about D4, D5, D7 like this. Experimentally, it is in the del T is equal to 4 by 9 del 0. This is all about the tetrahedral complex. Next, I will explain about the limitation of crystal field theory. First point is this theory unable to explain the covalent character of metal ligand bond. Second point is we know that the negative charged ligands have more repulsion to the valence electron of the central metal ion or atom, but they are present below the spectrochemical series. So these are the limitation of crystal field theory. Next I will explain about the factors affecting the magnitude of crystal field splitting. What are the factors affecting the magnitude of crystal field splitting? First is your nature of the ligand. Strong field ligand have more repulsion to the valency electron of the central metal atom or ion. So, in case of strong field ligand, the crystal field splitting is more. That means in case of strong field ligand, the crystal field splitting is more. On the other hand, in case of weak field ligand, the crystal field splitting is less. Next point is the ligand having more negative charge and less size have more crystal field splitting. Next point is the crystal field splitting increases with increasing in the oxidation state of the central metal atom or ion. Crystal field splitting also depends upon the size of the d orbital. If the size of the d orbital increases, then the crystal field splitting also increases. Crystal field splitting in case of octahedral complex is double of the crystal field splitting in case of tetrahedral complex. So we can write del T is equal to 4 by 9 del 0. These are the factors affecting the magnitude of crystal field splitting. Next I will explain about the application of crystal field theory. First application is to explain the color of coordination compound. In case of octahedral complex, we know that this is your T2G set of orbital and this is your EG set of orbital. This is your one set of d orbital. This is your another set of d orbital. In case of octahedral complex, what will happen? The electron transfer from T2G to EG. Either is or dt transition will be possible, and the complex shows a particular color. If the ligand is removed, there is no possibility of dt transition. Either is the compound is colorless. Second application is it also helps to explain the magnetic character of a complex compound, whether the complex compound belongs to paramagnetic or diamagnetic. If the coordination compound having unpaired electron, then that type of coordination compound are considered as paramagnetic. If the coordination compound do not have any unpaired electron, then the coordination compound are considered as diamagnetic in nature. Magnetic moment mu equal to root over of n into n plus 2 Bn. By this formula, we can able to calculate the magnetic moment of a coordination compound. These are the application of crystal field theory. Next, I will explain about the importance of coordination compound. There are large number of application of coordination compound. First application is in quantitative and qualitative analysis. Second application is your in extraction of metal. Third application is your in biological system. These are the different application of coordination compound. In biological system, generally we think that vitamin B12. Vitamin B12 is a coordination compound. In extraction of metal, generally we think about the extraction of nickel. In quantitative and qualitative analysis, generally we think about the estimation of Ca2 plus and Mg2 plus by the help of ethylene diamine tetraacetic acid. These are the different importance of coordination compound. Now I will solve some question. Question number 1 is your predict the number of unpaired electron, magnetic character, magnetic moment, and del zero value for the following compound. Number 1 is your CrH2O 6A 2 plus. Number 2 is your CrCN6A 4 minus. In this case, the chromium exhibit in +2 oxidation state. The atomic number of chromium is 24. The electronic configuration of chromium is 3d5 4s1. The electronic configuration of Cr2 plus is 3d4 4s0. This compound belongs to octahedral. For octahedral complex, according to crystal field theory, T2G set of orbital is present below, EG set of orbital is present above the barycenter. This is your EG set of orbital, this is your T2G set of orbital. Water is a weak field ligand. Due to weak field ligand, the del zero value is very small as compared to the pairing energy. So I can arrange the 4 electron present in the d orbital like this. This is the number 1 electron, 2 electron, 3 electron. Due to less del zero value as compared to the pairing energy, the 4th number electron present here. According to this diagram, the number of unpaired electron equal to 4. Our aim to find out the number of unpaired electron. So we can write the number of unpaired electron equal to 4. Next is your find the magnetic character. Here all the electrons are unpaired. So the magnetic character of this complex is your paramagnetic in nature. Next is your magnetic moment. We know that magnetic moment mu equal to root over of n into n plus 2 bm. Now put the value of n. Here n is your 4. So I can write mu equal to 4 into 4 plus 2 bm. That means I can write root over of 24 bm. Next is your find the del zero value. We know that this is your plus 0.6 del 0. This is your minus 0.4 del 0. There are 3 electrons present. So we can write del 0 is equal to 3 into minus 0.4 plus there are 1 electron present in each set of orbital. orbital, so we can write 1 into 0.6. That means I can write minus 1.2 plus 0.6. So we can write minus 0.6. According to the question, the number of unpaired electron is your 4. Magnetic character of this complex is your paramagnetic. Magnetic moment is your root over of 24 bm. Next is your del 0 value is your minus 0.6. Now I am to find out the all terms for this compound. Here the chromium exhibit in +2 oxidation state. The atomic number of chromium is 24. The electronic configuration is 3d5 4s1. The electronic configuration of Cr2 plus is 3d4 4s0. Here Cn is the strong field ligand. As a result, the del 0 value is more than the pairing energy. So I can arrange the 4 electron present in the d orbital like this. First electron present here, second electron present here, third electron is also present here, but the fourth number electron is present here because in this case Cn is the strong field ligand. As a result, the del 0 value is more as compared to the pairing energy. So the fourth number electron bound to pairing here. From this diagram, it is clear that the number of unpaired electron is 2. The magnetic character is paramagnetic due to the presence of unpaired electron. Next time is find out the magnetic moment. Mu is equal to root over of n into n plus 2 bm. Here n value is 2, so I can write mu equal to 2 into 2 plus 2 bm. That means I can write mu equal to 2 into 4 root over of bm. That means I can write root over of 8 bm. Next point is find the del 0 value. Look at that, here 4 electron present in the T2G set of orbital. So here I can write 4 into minus 0.4. There is no electron present in the Ag set of orbital. So I can write this term. Now del 0 value is equal to minus 1.6. In this question find the number of unpaired electron. Here the number of unpaired electron is 2. Next question is your magnetic character. This is your paramagnetic in nature due to the presence of unpaired electron. Next question is your magnetic moment. The magnetic moment is your root over of 8 bm. Next is your find the del 0 value. The del 0 value is your minus 1.6. Next question is your explain why TiH2O 6A 4 plus is a colorless complex ion while TiH2O 6A 3 plus is a colored complex ion. If you think about the complex ion TiH2O 6A 4 plus, in this case the titanium exhibit in 4 plus oxidation state. We know that the atomic number of titanium is 22. The electronic configuration of titanium is 3d2 4s2. If you think about the electronic configuration of Ti4 plus, then the electronic configuration is 3d 0. Look at that. In case of Ti4 plus, there is no unpaired electron. That means there is no possibility of dd transition. As a result, the complex ion TiH2O6 4 plus is a colorless complex ion. On the other hand, if you think about the complex ion TiH2O 6A 3 plus, in this case the titanium exhibit in +3 oxidation state. The electronic configuration of titanium is 3:2 4s2. If I want to draw the electronic configuration of Ti +3, then I can write 3d1 4s0. Look at that. In this case, one unpaired electron present in the d orbital. As a result, in this case, dd transition will be possible. That's why this complex ion shows a particular color. This is all about your coordination chemistry.